This video is a review of magnetism for AP Physics 2. I'd like to start out by talking a little bit about the origins of magnetism, and that is when charges are moving, and they're always moving inside of all of the particles that make up matter. The motion of those charged particles cause there to be small magnetic dipole moments that exist inside of all atoms in all materials. And I've drawn one of these up above, so you can imagine that maybe there's some charges moving around, and because of that they create a little dipole moment, a little magnetic field that's oriented in a particular direction due to the movement of those charges. Now, in most materials, all of those dipole moments are oriented randomly. Maybe you could imagine a chunk of material where the dipole moments are just pointing in all random directions. And because of the random orientation of those dipole moments, they all sort of cancel out, and none of those small magnetic effects add up to produce anything measurable. And so we say that most materials are not magnetic. But there are some materials that are what we call ferromagnetic materials, and ferromagnetic materials, things like iron and nickel and cobalt, have what we call magnetic domains, and they are places in a material where maybe a section of that material has several dipole moments that are all aligned with one another, and then maybe there's another domain that points in a separate direction where there are several dipole moments that are lined up with one another. And maybe the separate domains are aligned differently, but within the domain there are dipole moments that are aligned with one another. So there are some materials that behave this way. And what happens is, if I place this ferromagnetic material in an external magnetic field, then it's easy for those domains to become aligned with one another. And so if I have an external field, a magnet, or something that will allow me to move those domains, then the material can become magnetic. And so most importantly, there are some materials which, due to the random orientation of their dipole moments, they are not magnetic, and then some, when I have an external field, I can turn it into a magnet by aligning the domains inside of the material all up with one another. Another thing that we learned is that if you cut a magnet in half, then the two new pieces of the magnet will still have both poles. And in fact, no matter how many times you cut up a magnet, it will always have a north and a south pole. One pole has never been observed to be separate from the other. And so for that reason, any material must have, if it's magnetic, must have a north and south pole. And those are just names that we give to things, but similar to, we call charges positive and negative, we call poles north and south. And it helps us distinguish between the poles that attract and the poles that repel, which work the same way that charges do. Like charges repel and opposite charges attract, and the same thing goes for poles. Now, if I have a magnet, then it has a well-defined north and south pole, and around the magnet, in the space surrounding the magnet, there is a magnetic field. And that magnetic field is an indication that if I put something that's magnetic nearby, that it would feel a force from that magnetic field. So those lines are lines of force. And one thing that we learned about magnetic field lines is that they seem to start at the North Pole and go to the South Pole. But then, of course, one of the things that we learned about magnetic fields, which were different from electric fields, is that they do not start and end. So electric field lines start and end on, positive or negative charges, but electric field lines are loops. They are loops that go from one pole to the other and then through the magnet. And so in this case, the magnetic field lines should be drawn as continuing through the magnet like this. Now I'd like to just mention a little bit about Earth's magnetic field, and that is, if I take a compass and I take it out, the north end of that compass will point toward the north geographic pole. But we know that for a bar magnet, the north end of the compass points toward the south end of the magnet, or at least the magnetic field lines that emanate from the north end of the compass, or sorry, the north end of the bar magnet, will point from that north to the south pole. And so if the compass is pointing to the north, that must mean that the north geographic pole is the south pole of Earth's magnetic field. Now I'd like to talk a little bit about magnetic force. And the origin of magnetic force is a little bit more strange than what we've seen with some other forces, and that is, in order for an object to experience a magnetic force, it not only has to be a charged particle, but it also has to be moving. And so when you have a charged particle that's moving, it generates a magnetic field. Just like as we said when we were talking about the magnetic domains and the magnetic dipole moments, a moving charged particle creates a little magnetic dipole moment. Therefore, anytime I have a charged particle that is moving, it's going to generate its own magnetic field. And if it has its own magnetic field, if that charged particle is placed into another magnetic field, then those two magnetic fields will interact. And what happens is the charged particle experiences a force. And we call that force a magnetic force. And sensibly, that magnetic force depends on the charge. So that is just the magnitude of the charge. V, which is the speed of the particle measured in meters per second. B is the strength of the magnetic field that the charged particle is in. So not the strength of its own magnetic field, the strength of the magnetic field that the charged particle is in. And lastly, theta represents an angle between two vectors. And in this case, we should think about what the two vectors are. Now, Q is just the charge on the particle measured in coulombs, but V is the velocity of the particle, and that can point in a particular direction. And B is a field. It's the magnetic field strength. And so that's also a vector. So theta represents the angle between V and B. And as I've shown down in the bottom right-hand corner, we remember that if theta equals 90 degrees, then those two are perpendicular, and the sine of 90 degrees is equal to 1. And for that reason, we can just use the equation FB equals QVB only in cases where V, the motion of the charged particle, is perpendicular to the direction of the magnetic field. Lastly, I'll mention that the SI unit of magnetic field is the Tesla, which is defined in terms of other units. But most importantly, just know that the SI unit of magnetic field is Tesla. And when we find the product of all those things, then we have determined the magnetic force on the object. But of course, this equation is an equation that tells us the magnitude of the magnetic force. The direction of the magnetic force is found using the right-hand rule. So now I'd like to talk a little bit about how we determine that direction. And so if you remember, the right-hand rule for determining the direction of the magnetic force on a charged particle is done in the following way. This is one of a few variations that can be used to get the direction correctly. So first, I'd like for you to point your fingers in the direction of the velocity of the charged particle. And then I would like for you to curl your fingers in the direction of the magnetic field. And so if we're using our right hand for the magnetic field and charged particle that are labeled number 1 on the left-hand side, my fingers are pointing to the right of the screen, and the dots represent a magnetic field that points out of the screen. And so I need to curl my fingers out of the screen, which means I need to turn my hand upside down. And so now my fingers are still pointing to the right, and I'm curling my fingers out of the screen. And when I do that, my thumb is pointing toward the bottom of the screen. And so that means the force on the charge, if it is positive, will point downwards. If it is a positive charge, then the force will point downwards. If this were a negative charge, the force points in the opposite direction, which would be upwards. Okay. But of course the charge has to be either positive or negative, so only one of those forces actually exists. Let's move on and do these next three. For charge number 2, which I have drawn near the top, the velocity of the charged particle is toward the top of the screen. The magnetic field is going into the screen. The X's represent a magnetic field that's going into the screen. So I need to point my fingers up and curl them into the screen, and you'll find the thumb on your right hand is pointing to the left. And so again, this is the force that a positively charged particle would experience. A negatively charged particle would experience a force in the opposite direction, which is to the right. Lastly, let's talk about numbers 3 and 4. So for number 3, the velocity is toward the top of the screen, so my fingers point toward the top of the screen. The magnetic field is to the right, so now my fingers should be curling to the right. And what this means is, right now, with your fingers toward the top of the screen, your palm is probably facing downward, and now you need to rotate your hand so that way your fingers can curl to the right. And now if you curl your fingers to the right, with your fingers originally pointing in the direction of the velocity, your thumb should be pointing into the screen. And so the way that I would represent the force on this charged particle is I would draw a X that represents, and I would write FB next to it, which represents that the magnetic force is going into the screen if it's a positive charge. If it's a negative charge, then the magnetic force points out of the screen. And so I can represent that with the dot or the X in the same way that I represent the magnetic field with dots or X's for magnetic fields that are perpendicular to the velocity. Lastly, let's try the right-hand rule on number 4. So I point my fingers in the direction of the velocity, and now I need to curl my fingers in the direction of the magnetic field, and it's tempting to continue to curl them backwards, but what you will find is that the right-hand rule breaks down when the velocity of the charged particle is pointing in the same direction as the magnetic field. And the reason for that, well, maybe not the reason for that, but one thing that supports that is if I make measurements of charged particles, I really do get that QVB sine theta gives me the correct expression for the magnetic force. And hopefully you can see in this case that theta represents the angle between V and B, and in this case, for number 4, theta is equal to 0. And if theta is equal to 0, then that means the force is equal to 0. And so before you even do the right-hand rule, if you see that there's a charged particle, whether it's positive or negative, that points along the direction of the magnetic field, then you should immediately conclude that the force on that charged particle, the magnetic force on that charged particle, is 0. So we just looked at the case of, just a static, direction of the charged particle in a magnetic field, but now I'd like to talk a little bit about the motion that a charged particle would have experiencing that magnetic force. And what we've learned is that those magnetic forces are always exerted at right angles to the velocity. And so for that reason, the charged particle will always experience a force that causes the object to move in a circle. And we know that forces that cause objects to move in a circle, forces that are center-seeking towards the center of a circle, perpendicular to a velocity, are called a centripetal force. And so in essence, a charged particle in a magnetic field experiences a centripetal magnetic force from that magnetic field, causing it to move in a circle. And we learned that the charged particle goes around in a circle with maybe a well-defined radius r, and V and FB are perpendicular. And we learned the relationship between the radius of that circle and the speed of the particle by writing a Newton's second law equation. The Newton's second law equation, which says the sum of the forces is equal to the mass times the acceleration of that charge. Well, if the magnetic force is the only force acting on the charged particle, then the only force we have to write is the magnetic one, which is QVB. And that one force is equal to the mass of the particle times the acceleration. And since it's moving in a circle, the acceleration is a centripetal acceleration. And centripetal accelerations are always equal to v squared, the straight line linear speed, divided by r, which is the radius of the circle. And the reason why this is such an important relationship is because it would allow us to solve for the radius of the circle, the velocity of the particle, and very importantly in some cases the mass of the particle. And so this is an equation that if you remember how to get here, there's a lot of important quantities that could be measured. After learning about the movement of charged particles and their interaction with magnetic fields, we started to think about this idea that if I have a wire and the wire has charged particles moving in it, right? It has a current flowing through it. It's a current carrying wire. Then it should also experience magnetic forces because essentially a wire has just moving charges and charges experience a force from magnetic fields. And so we looked at this in a couple of different ways. First, we said, what happens if I have a current carrying wire in a magnetic field? So for this, I'm looking at the left-hand side of the screen, and I see that about half of this wire with current is in a magnetic field and the other half is not. So there is an equation that is for the magnetic force exerted on that wire due to an external magnetic field. And the force from that external magnetic field on the wire is dependent on the current. It is dependent on the length of the wire that's in the magnetic field, which I've shown above in green. It's dependent on the strength of the magnetic field, and it is dependent on the angle between the orientation of the wire and the magnetic field. So here the wire is pointing to the left and to the right, and the magnetic field is pointing into the screen, and for that reason they're perpendicular. So just like before, the sine of 90 degrees equals 1, and we can just use the equation ILB. So importantly, I want you to appreciate that this is the force that is exerted on that wire due to the external magnetic field that I've drawn with the white X's. But wires themselves have a magnetic field around them. And for this we learned a slightly different right-hand rule. We learned that if I point my thumb in the direction of the current, then my fingers will wrap in the direction of the magnetic field that surrounds that wire. So if I point my thumb to the right for this wire that's on the right-hand side, then my fingers are curling around that wire, coming toward me on the front side of the wire and going away from me on the back side of the wire. Again, a new right-hand rule where you start by pointing your thumb in the direction of the current. And this is different from the magnetic field that we were analyzing on the left-hand side. We were ignoring the magnetic field from the wire itself. We were talking about an external field. And if you want to do the right-hand rule for the equation on the left, then you point your fingers in the direction of the current, you curl your fingers in the direction of the magnetic field, and you again point your thumb in the direction of the force. Lastly, I'd like to mention that we investigated an equation for the magnetic field strength around a wire, and we learned that the magnetic field around the wire depends on some constants, the magnetic permeability and 2 pi, but more importantly, there's a relationship between the magnetic field strength and the current. It's a proportional relationship. One increases, the other increases, which makes sense, right? If I increase the current in the wire, the magnetic field gets stronger. And what makes even more sense is that there is an inverse relationship between the magnetic field strength and the distance away from the wire. So the further I get away from the wire, the weaker the magnetic field becomes. And both of those are just direct relationships. One is proportional, one's inversely proportional. There's no squared terms. So if I go twice as far away, the magnetic field is half as strong. If I increase the current by a factor of 2, the magnetic field is twice as strong. The last few topics that I'd like to talk about are related to magnetic flux. And we know in general what the word flux means. Flux describes the rate of flow through something. And so most recognizably, we have described flux as being the amount of magnetic field that is going through a particular loop of wire, for example. And we use the Greek letter phi to define flux. And B represents the strength of a magnetic field. A represents the area through which the field is going, and of course theta represents the angle between the direction of the magnetic field and the orientation of the area through which the field is going. And most importantly, in the top right hand corner of the screen here, if I have a certain area through which there is flowing a magnetic field, when I'm talking about the orientation of the loop, or theta, I'm talking about the angle between that magnetic field, which is represented by these red lines, and a line that is perpendicular to the surface of the loop. So if you imagine that loop being a closed off surface, and I had a little arrow that was pointing out from the surface of that loop perpendicular to its surface, then you would see that the magnetic field lines and the line perpendicular to the surface are in fact pointing in the same direction. And in that case, the angle between those two things is 0, and therefore the cosine of 0 equals 1. And this should make a lot of sense. When the magnetic field is flowing in the direction of the surface of that we're talking about, then the flux is the greatest. And in the case where those two things are perpendicular, cosine of 90 degrees, then we should expect that the flux is 0 because they're pointing perpendicular to one another. And so I have an example here of a horseshoe magnet where maybe there's a magnetic field that goes between those two poles of that horseshoe magnet. And we've seen examples of a little loop of wire where it is being turned. And as it's being turned, due to the fact that the coil is rotating, the orientation of the surface relative to the unchanging magnetic field is changing. And so because of the orientation of the coil changing, the amount of flux going through the coil is changing. So the magnetic field is not doing anything, it's just pointing from north to south. But the coil moves, causing the flux to change. And this led us to Faraday's law, because if I hook up a couple of wires or a meter to that coil, then I would measure an EMF, or maybe a current flowing in that loop of wire. And so what happens is, as the flux changes due to the rotating coil, then that change in flux produces an EMF in the wire. And so clearly there's a relationship here between electricity and magnetism. I can use a magnet to generate a current in that wire, and we've also seen examples of using electricity to generate magnetism, right? We just talked about how if there's a current in a wire, there is a magnetic field generated around the outside of that wire. So it's possible to have magnetism generate electricity, and it's possible to generate, go through that in the opposite process. Perhaps one of the more difficult topics that we've studied this year is Lenz's Law. And Lenz's Law says that if there is a changing flux, and we just talked a little bit about changing flux, that changing flux is going to induce an EMF, an electromotive force, such that it creates a current, and the magnetic field produced by that current will oppose the change in the flux. So we have a changing flux that creates an EMF. If there's an EMF present and there's a closed loop, then I can always get a current. And if there's a current, then things with currents in them create magnetic fields. And Lenz's law says that the orientation of that magnetic field will point in a direction such that it will oppose the change in the flux. So I'm going to try to remind you of an example that we saw. And that is when a magnet is dropped down a pipe, a pipe that's made of a conductor. So maybe you've got like an aluminum pipe or something like that, or something that can conduct a current, allows some charges to move. As it goes down, the magnet slows down drastically. You expect the magnet to fall at the bottom of the pipe, and it takes considerably longer for it to fall out. And so what happens? Well, first, we know that as the magnet falls, the amount of flux at below the magnet will be increasing as it approaches a particular point in the pipe. So for example, I'm going to point out this point right here. Maybe we're paying attention to a particular point on that pipe, and as the magnet approaches that point, the amount of flux in that part of the pipe is going to be increasing. And how do I know that? I know that because as I get closer to the pole of a magnet, the magnetic field gets stronger, and one way we represent that is by the number of magnetic field lines that are passing through there. So in that first green circle, there's a lot of magnetic field lines. If I go a little bit further out, there's fewer and fewer magnetic field lines. So of course the magnetic field is getting stronger as you get closer to the pole. So as the magnet approaches that red line that I've drawn, the magnetic flux is going to be increasing. So I know that the magnetic flux is pointing downwards, and I know that the change in the flux points downwards. And how do I know that the change in the flux points downwards? Let's look at number 2. If the flux is increasing, then the change in the flux must also be increasing. Okay? A change in flux is the final flux minus the initial flux, or we could think of it that way. And therefore, if the flux is increasing, then the final flux will be greater than the initial flux. So that's not so important in terms of whether it's positive or negative, but it is important that you know that the change in the flux has to point in the same direction as the flux if it's increasing. I'm going to say that again. The change in the flux has to point in the same direction as the flux if the flux is increasing. The reason why, or one way that I like to understand that is if I have the velocity of some random object pointing to the right, and the change in the velocity also points to the right, then I know that its speed is increasing. Right? Because a change in velocity represents acceleration. And so if the acceleration of an object points in the same direction as its speed, it will speed up. If the acceleration of an object points opposite the direction of its speed, it will slow down. So in this case of the magnet in the pipe, the flux is increasing at that red line. And if the flux is increasing, then the change in the flux has to point in the same direction as the flux. Lastly, if I know, and this is getting us to number 3, I know that because of that changing flux, there's going to be a current produced in this pipe. And the direction of that current needs to create a magnetic field that will oppose the flux. And since the change in the flux points down, then that magnetic field needs to point up. Which means that there needs to be a magnetic force that points up. And the way that I get an upwards magnetic force is I need to move my fingers in the direction of the current and figure out which way my thumb would point, and that is in fact upwards for a current that would be flowing in this direction. And so apparently as that magnet falls for this orientation, the current will be flowing to the right across the outside of that pipe, and therefore exert an upwards magnetic force on that magnet, and that upwards magnetic force will cause the magnet to slow down. The last thing I want to say about this is that we also understood this much more simply using conservation of energy. I know that as a magnet falls down a pipe, it's going to create an EMF in that pipe, and the EMF causes a current. And the current is the flow of charge. And so if the magnet is causing charges to flow, then it has to lose energy in order to allow those charges to flow. After all, the electrons that are in that pipe that are moving, they have to get their energy from somewhere. And so the electrons are moving, and that movement of electrons by conservation of energy allows us to understand that inevitably the magnet must slow down. The last topic I'd like to remind you of is very much related to what we just talked about, but it's called motional EMF. We talked about how when a conductor moves through a magnetic field, when a conductor moves in a magnetic field, there is an EMF that is induced, and we know that this is possible because if on the left-hand side here I just imagine this blue particle to be an electron, if the charged particle is moving, or sorry, if this conductor, which is represented by the yellow square, is moving through the magnetic field, the magnetic field points out of the board, the velocity of that conductor is pointing to the right. Let's look at one electron that's in this conductor. If there's an electron there, the velocity of the conductor is to the right, so my fingers point to the right. The direction of the magnetic field is out of the screen, so I need to point my fingers to the right, but then turn my hand so that way I can curl my fingers out of the screen, and my thumb would point down. So my thumb points in the direction that a positive charge would feel a force, but this is an electron. So the force on the electron is up. And so you can imagine, if there are electrons in this conductor, there's a tendency for those electrons to go toward the top of the conductor. There's a tendency of positive charges to go toward the bottom of the conductor. For that reason, there's a potential difference that is created across this conductor. And as a matter of fact, if I took that conductor and I attached a resistor to it and made a closed loop, there would be a current that would flow in there. If this were a light bulb instead of a resistor, the light bulb could turn on potentially. And so this is a great example of a conductor moving through a magnetic field, and it creates an EMF. Now, if I have the right scenario for it to create a current, that I have a closed loop, then it also creates a current. But otherwise, that potential difference is just there. And we looked at the equation for this EMF that's produced across the conductor, and we found that it's equal to the strength of the magnetic field times the speed of that conductor, which means the faster it moves, the greater that EMF will be, and the length of the conductor. And here the length just represents, how long that conductor is. And finally, I want to look at a little bit of an example here on the bottom to remind you of something that we learned about. I have a little cart here that has a loop of wire on the top, and as that cart gets pushed through a magnetic field, it enters the field, then it's in the field, and then it's leaving the field. We learned that what happens as it enters, as it leaves, and while it's in it is a little bit different in each case. So first off, I want you to take the conductor that I've drawn up above and think about what's happening on the right-hand side of this first picture here. There's a piece of conductor, and here the magnetic field points in the opposite direction, so maybe it makes sense that I have drawn the places where positive charge and negative charge would end up in the opposite sides of the conductor. But let's make sure. The velocity of this cart is to the right. An electron that is right here on the right edge of this conductor would, because of its velocity to the right and the magnetic field being in, if it were positively charged, it would feel a force up. It's negatively charged, so it feels a force downward. And so electrons will want to go down. Because of this, there's a potential difference induced across the two sides of that conductor, and it is going to cause a current to flow counterclockwise in that loop. Now let's look what happens as it's leaving. The symmetry of this is exactly the same, and so for that reason it still produces an EMF where the positive charges are on the top and the negative charges are on the bottom. This time, however, the current flows clockwise. And then while both edges of the loop are in there, while both edges of the loop are in the magnetic field, there is simultaneously a current that wants to flow clockwise and a current that wants to flow counterclockwise. And what ends up happening is those two currents will cancel one another and there's no current. So actually we only get a current while it's entering or while it's leaving the magnetic field. While the whole thing's in there, we don't get any current at all. And maybe you remember if we have a little ammeter attached to this, while it's entering, we might get some, positive current maybe. And then while it's leaving, maybe we get some negative current. And while it's inside of the magnetic field, that current would read 0. And so in general, you should remember that when a conductor moves through a magnetic field, there's a potential difference made across it. And that potential difference can drive a current if it's connected in a closed loop. But the current is only generated in a loop of wire while it's entering or leaving the magnetic field, because while the whole loop is in there, it kind of creates opposite currents that want to move charge in opposite directions, and so those effects cancel each other out. Also remember that the faster the thing goes, the greater the EMF is going to be, therefore the greater the current will be.